Alrighty. Today we're going to look at the rational roots theorem. Okay, but I'm not going to get into what the theorem actually says. All right, I'm just going to kind of show you how we're going to be using it. Okay. What it says is, it's not. I mean, well, it's important, but you'll get an idea of what it says by how we're going to use it and stuff like that. Okay, remember again, we started this unit looking at cubics. You're transforming them left, right, up, down, vertical stretching, reflecting over the x-axis, that kind of stuff. And we quickly moved on, though, to just talking about polynomials in general. So higher degrees than 3, right? Any polynomial. We talked about how, we sketched the graphs of those polynomials first, right, by finding the end behavior, the zeros, the middle behavior, getting the sketches. Then we quickly moved into those solving, okay? Those polynomial equations, and specifically trying to factor. Factoring is a big thing because, when we were sketching the graphs, all the graphs that we were sketching, they were already factored for us, right? But most of the polynomials you're going to run across, right, if you ever, when you run across polynomials, they're not going to be factored for you. So we have to come up with ways to factor them, all right? Which can be tricky, as we've seen, right? We can use grouping, we can use greatest common factor to factor, we can use like difference of squares, sum of cubes, difference of cubes, all these different situations, but even still, there are problems that we can't factor, right? We saw that we also have like synthetic division and long division, though, to help us divide, but the problem is with those is you need to know what you're dividing by in the first place, right? We don't always know, looking at a polynomial, what I should divide by. And so the rational roots theorem provides a limited list of guesses for us to make. Okay, about what the zeros, what the roots could be, okay, what we could potentially divide by, okay, and so that's kind of the key thing to remember here is that the rational roots test gives us a list of possible rational roots for a polynomial. Okay, so write that out here. Okay, possible rational roots. So rational, right, refers to the group of numbers known as the rational numbers. Rational numbers can be written as fractions, right? A over b, where a and b are both integers. So, 1 over 3, right? 10 is a rational number because it's 10 over 1, right? So what are some irrational numbers? Does anyone know an example of an irrational number in here? Pi, yes. What makes pi irrational? Like what kind of behavior, what kind of behavior does pi exhibit? It doesn't, it goes on forever, but 1/3 goes on forever too, right? It's 0.333333. Why is pi irrational, but like 1/3, even though it goes on forever, rational? So what's the difference there, yeah?
Pi goes on forever, but it never repeats.
Yes, never repeats regularly. Exactly right. 0.33333, right? It repeats. It goes on forever, but it repeats. Pi goes on forever, never repeats. Okay, not in a regular fashion at least. Okay. Same thing with like square root of 2. That's irrational, right? Anything that's like a square root that's not a perfect square, kind of thing. That's going to be irrational. So anyway, this is going to give us a list of all the possible rational roots. Since there are other kinds of numbers besides rational roots, this still is not going to provide us a foolproof way to factor a polynomial, okay? But this is the limit to which we will be going, I guess. Like we won't go any further beyond this, okay? There are like other analytical ways to like get zeros and stuff like that. We're not going to do that though. This is kind of the limit of where we need to go, okay? So we won't go any further than this. Okay, so let me show you an example of how this is going to work then. So given x to the third plus 2x squared minus 11x plus 12. What are the possible rational roots? Oh, and by the way, the roots, okay, what other synonyms do we have for the word roots in math class, right? Roots is also the same thing as what? Not exponents. X something, though. X, it's where the graph crosses the x-axis. So that means we could also call roots x-intercepts, right? Or also what? I think I heard it. Zeros as well, okay? So roots, x-intercepts, and zeros are all talking about the same thing, where the graph crosses the x-axis, okay? So these roots, we're looking for where this thing crosses the x-axis, okay? And we're going to come up with a possible list of rational roots, okay? Because knowing the roots allows us to then factor, right? Come up with the factors. Okay, because the factors and the roots are closely related to each other. So anyway, again, let's just kind of appreciate what we're trying to do here, right? If you look at this, would we be able to factor this by grouping?
Yeah.
We could group it, okay? But the problem is, if I group this first one, I'll be able to pull out an x squared. I'll have an x plus 2 left behind. But here, if I pull anything out, I'm not going to have an x plus 2 left behind. So while you're right, we can group, it's not going to be helpful, right? It won't be helpful. All right, is there a GCF we could pull out here? No, there is not. Okay, so that fails us. It's not quadratic, so we can't factor it like a quadratic. It's not a difference or a sum of cubes. Can't use that. It's not a difference of squares. Can't use that. We don't know any factors, so we can't, like, pull one out. We're not told what one is. So we're kind of stuck. But we're going to come up with a list of possible roots here. Okay, and here's how we're going to do that. Okay, we need to identify two numbers in our polynomial. We're going to identify q. Q is the lead coefficient of our polynomial. Okay, and then there's p, and p is the constant term. Okay? So for this particular example, q is what value? What's our lead coefficient here? 1. So q is 1 in our example, right? Right there. There's q. Okay. What is p in our current example here? 12. Okay. There's our p. Now, I'm not really sure why they're designated this way. Okay, we do p and q are the typically used like letters to help us like identify these things, but I'm not sure why we put q as the front one and p as the back one, because p comes before q alphabetically, but I'm not sure. Anyway. Okay, so once you've identified these numbers, then here's how we're going to use them. Okay, then every possible rational zero, okay, will have the form, okay, we'll have this form. Factors of p divided by factors of q. Again, possible rational zero. So let's talk about our factors of p then. So p is 12. What numbers divide 12? What numbers are factors of 12? What numbers divide 12? Okay, 6 and 2. 3 does. Okay. What else? And I heard 6 as well, right? Okay. What else? 4. What else?
12.
Yeah, don't forget the obvious ones, right? 1 and 12. Yeah. Any more? 1, 2, 3, 4, 6, 12. Any other numbers that divide 12 evenly? Yeah. So this is important too, right? That we can recognize when we need to stop trying to list numbers out, okay? So we want to make sure that we're sure. But the answer is, yeah, that's it. Okay? What about factors of Q? Q is 1. So what are the numbers that evenly divide 1? 1. Okay? So if this polynomial has rational zeros, then they will be, the rational zeros will be in this form. Oh, by the way, sorry. I put the plus or minus in front because we can divide 12 by positive or negative 1, right? We can divide 12 by positive or negative 2, positive or negative 3, positive, you get an idea, right? Same thing with Q of 1, right? We can divide positive 1 by 1 or negative 1. So that's why you have to put the plus or minus in there. So here then would be a list of all possible rational zeros. Okay, so again, our zeros are going to have this form where it's going to be a factor of p divided by a factor of q. Okay, so 1 over 1 is just going to be 1, so we have plus or minus 1. 2 over 1 will be 2, again, plus or minus 2. 3 over 1 is 3. 4 over 1 is 4. 6 over 1, 6. 12 over 1 is 12. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We have 12 candidates for zeros. Okay? 12 possibilities here that could be zeros of our polynomial up here. Okay? How can we actually determine if any one of these numbers is a zero? What could we do? Equal it? What do you mean by equal it? Not sure? Okay. I mean, you're onto something there. What? Okay, we can graph the equation and just check and see which ones work for the zeros. Yeah, that would work. We could also sub these in to our polynomial and see which ones give us 0, right? For the zeros, right? Exactly. Okay. We could also do synthetic division and plug these in for synthetic division and see, okay, which one of these give us a 0 remainder. That's another option too, right? Okay. Let's try one more here. We'll do one more just with the rational roots theorem, and I'll show you how we then use these results. Okay, so I'm going to, again, these are just like our list of possible zeros. So I'm going to, again, come up with a new list of possible zeros for a new problem, and then I'll show you how we're going to use that for what we're going to do tomorrow and Friday, too. So, again, if we're trying to list the possible rational zeros, it means the possible, possible zeros, possible roots, possible x-intercepts here. Okay. We have to identify our p and our q again, right? So factors of p here over factors of q. Okay. What is our p in this problem? Okay, remember p is the constant term. So what's p in this case? So yeah, -6. Okay, so there's our p. Okay, What is our Q in this case? 2. Okay, very good Q. Get the idea, though. Ugh, even worse. All right, so anyway, what are the factors of 6? Okay, 2, 3, 1, 6, or 6, 1, yep. I'll put them in order there, okay? I like to put them in order. You don't have to. Over, what are the factors of 2? 2 and 1. Okay, now that's different, right? Unique, we have 2 factors for Q, as well as, 4 factors for P there. So let's see how it's going to change things up. So let me list. Yep, P's on top. The factors of P are on top. Gotcha. List of the possible rational zeros. So again, our zeros will have this form, but what actual zeros are we talking about here? Well, we'll have 1 over 1, which is 1. We'll have 2 over 1, which is 2. We'll have 3 over 1, which is 3. We'll have 6 over 1, which is 6. But what else we have? We're going to have 1 over, 1/2, 1 over 2, so 1/2. Then we also have 2 over 2, but what's 2 over 2 really? It's 1. Do I need to list that? Because I already have it, right? So I don't have to do 2 over 2. What about 3 over 2? Do I already have 3 over 2? I do not have 3 over 2 yet, so I'm going to put 3 over 2. Okay, and then 6 over 2. What's that simplify to be, though? 3, and I already have 3, right? So here are our possible rational zeros here. Okay? So it is these numbers that we're going to use to help us try and factor this polynomial here. Okay? All right, so let me show you how we're going to do that then. Okay, I'm just going to show you this one example here. We'll do more of this kind of stuff tomorrow too. All right, so from this list, someone pick a number. 3. Okay, I heard 3. Let's try 3. All right, so we're going to guess 3 and see if that works. We're going to guess positive 3 here. So I'm just going to circle a little plus sign there. So we're going to put 3 in the little box for the synthetic division. Okay, across the top here, we're going to put our coefficients, right? So 2, 3, negative 11, and negative 6. Okay, leave a line. Okay. We'll drop the 2. 2 times 3 is 6. 6 and 3 makes 9. 9 and 3 is 27. 16 times 3 is 48. 42. Okay. Is 3 a rational zero of our polynomial? No. How do we know? There's a remainder. So, just like the Nazi in the last Crusade, we chose poorly at the end of the last Crusade. Indiana Jones. You guys ever see Indiana Jones? It's a good movie. It's a good one. It's a good one. Yeah. Yes. Yeah. Oh, yeah. No, it's pretty scarring for sure. That was Raiders. Well, he kind of he ages. Yeah, exactly. It's kind of similar kind of thing. Last Crusade. I never got that one. It's good. It has Sean Connery and his dad. He's looking for like the Holy Grail. One with a tomb. Okay. Oh, yes. Oh, it frightened me as a child. The second one, a guy pulls someone else's heart out. It's pretty cool. Anyway. That one's more intense, yeah. All right, folks. Guess again. All right, 2. So again, positive 3 didn't work. Let's try positive 2. Okay, let's try positive 2. Positive 2. So again, we'll start over with the 2, the 3, the negative 11, the negative 6. I'll leave a line, and we'll do our synthetic division here. Oh my gosh. Is 2 a rational zero?
Yes.
It is. Good guess. Okay, so 2 is a rational zero. Okay, great. But how many possible rational zeros are we going to have here? How many are we going to have? What's the degree of this thing? It's the degree is, of our original polynomial, it's 3. So that means there could be 3 zeros. We found one of them. So how many more do we have to find still potentially? 2. So I might still have to guess all these different all these numbers here to figure out which one works.
So you have to do each one of those to like
Potentially. But what's the result here? What is this translate to be? 2x squared.
plus 7x
Plus 3. Okay. Now, could we factor this one by hand? Would grouping work, for example? I mean, you could group the first two, you get an x squared out, but you'd have 2x plus 3 left over, and this is not going to be able to group and factor be a 2x plus 3. Okay? Grouping doesn't work here, right? Nor does GCF. So we had to resort to guessing to find one that works. But now we found that one work. Now we found one that works. We are now down to a quadratic. Can we factor quadratics? Yes. So we don't need to keep guessing here. Okay, we don't need to. We can just do the a times c method here. So 2 times 3 gives us the 6. Okay, we're looking for two numbers that multiply make 6, but add to make 7. 6 and 1. Okay, so we'll split up that middle term. Now we'll group. Okay, from the first group we can pull out a 2x. From the second group we can pull out a 1. Pull out the x plus 3s. We'll be left with 2x plus 1. Oops, I'm off the screen, sorry. So what are our other zeros here? Okay, we already got 2 as a 0, right? But if we take our polynomial here that's left and we set it equal to 0, right? What are our other zeros? Well, x plus 3 will be equal to 0, or 2x plus 1 will equal 0. And so that means if we subtract 3 from both sides here, we get x equals negative 3. And if we solve here, minus 1, divide both sides by 2. Okay, we get negative 3 and negative 1/2 as zeros as well. Okay, so you're close to the 3. We just need to do negative 3. Okay. Okay, so negative 3 and 1/2 are also zeros, or negative 1/2. Negative 3 and negative 1/2. So our 3 zeros are 2, negative 3, and negative 1/2. Okay. So that's how we're going to be using this rational roots test. Okay, we're going to come up with a list of zeros, and they're going to guess and check which one of those zeros works to hopefully then reduce down to a quadratic. And then once you get the quadratic, we factor that quadratic to get our other zeros. Okay, you could keep guessing and checking if you wanted to. Now, Liam kind of said this earlier, but I want to reiterate it too. Okay, we don't have to guess our zeros. What tool will we have available to us? The calculator. We can use the calculator to graph these polynomials if you really want to, okay? If you want to, miss out on all the fun of guessing, you could graph this and then just identify your zeros from the graph and use that to help you when you then guess which zero to pick from your list of possible zeros here. Okay? Let me just show you what I mean, right? If I graph this polynomial, all right, if I put this in, 2x to the third plus 3x squared, oh boy, mash the keypad there, plus minus 11x minus 6. let me finish this real quick and I'll let you go, yeah. Okay, can you see where our polynomial crosses the x-axis here? Where's it cross? -3, where else? -1/2 it looks like, and 2. And isn't that exactly the zeros that we found? 2, -3, -1/2. Okay? So you can also use your graphing calculator to help you with the guesses and stuff if you want. Because you will be able to use that. Okay? All right. If you want to go, Robert, go ahead. Your homework assignment, I'm done. Okay? And your assignment is going to be one problem. Okay? So I don't want to hear any excuses tomorrow. Mr. Wood, I can get your homework. You got plenty of time right now. Okay? I just got to remember what I posted. Oh, did I post it? I don't think I did. Page 252, number 1. That's in 7-1 is the section. Okay? That's it. So